Welcome back to another online lecture for Calculus 1. In this video, we're going to learn about a topic called linear approximations. All right, let's go ahead and get started. Linear approximations basically try to use derivatives to approximate some numerical values and simplify functions. This might not make a lot of sense right now, but it's an important technique in science and engineering once problems get a lot more complicated. Now, this might sound complicated using a linear approximation, but it's basically based off the equation of a tangent line. So despite some of the last topics that we've covered, this topic is usually considerably simpler for students. All right, before we get into what linear approximations are, let's consider kind of a motivating problem. All right, so suppose we're asked to approximate the square root of 4.05. Now, everyone should be able to give me a basic answer requiring really no calculation or time at all. We know square root of 4 equals 2. And since 4.5 is a little bit bigger than 4, we should expect the square root of 4.05 to be a little bit bigger than 2. If we make that a little bit more precise, we can say square root of 4.05 should equal 2, but then plus a small number, some decimal part. And what we're going to learn and see in a little bit is that small number comes from a derivative. All right, so as mentioned a minute ago or so, the starting place for linear approximations is the equation of a tangent line. So let's go back and review that before we move forward. So we think the setup is we have a graph of a function, and if we pick a point on that graph, we'll label it as x coordinate a, y value would be f of a. For this point on the graph, we have a tangent line that looks like that. All right, now the key idea with how linearizations or linear approximations work is if we look just around that point, notice we kind of circled a small portion of the graph right around that point. On the x-axis there, you have some values on the x-axis that are close to a. If we kind of stay within that small portion of x values near that point, the tangent line and graph are pretty close together. And that is pretty much the main idea that we're going to kind of encounter in a few different ways as we proceed. So notice within that circle, the black graph stays pretty close to the red tangent line. As soon as you go outside of that circle, as soon as your x values are now not close to a, the graph of the function and the tangent line are significantly far apart. Okay, so we're going to build off the equation of the tangent line here. We have our basic version there coming from point slope form, y minus y1 equals m times x minus x1. All right, and we're going to basically just manipulate that. We're going to add the f of a term from the left side to the right. So we're just adding f of a to both sides, and we get this expression. And we're going to translate that into what we're going to call the linearization. So we're going to give it a different formula. We're going to define the linearization of a function at an x value a to be this expression, L of x, that's denoting the linearization, and then equals this expression, f of a plus f prime of a times x minus a. So compare right above. This thing that we're now calling the linearization is really just the equation of a tangent line. All right, now before we get to how we're going to use linearizations for approximations, let's take a look at the important idea translated now into the language of using linear approximations. So if you think back above, we said that the tangent line in red is close to the graph of f of x, as long as the x values stay close. So we're going to translate that to say down here, f of x is approximately equal to the linearization when the x values are approximately equal to a. So that's kind of the same thing above. The graph and the tangent line are close when your x values are close to a. This important idea is going to be what allows us to use calculus to find approximations. Now, if we go back to that graph that we have above there, there is kind of an everyday phenomena we experience that kind of exhibits this idea of the tangent line and the graph being close. If you were to zoom in on that point right there, you can kind of see it there with the circle around it. If you zoom in really close to that point on the graph, eventually you're going to find that the graph and the tangent line look even closer. They're going to look indistinguishable as you zoom in closer and closer. Now, what this basically says is that a curvy function, if you zoom in close enough, is going to eventually look flat. Now, what's the everyday phenomena that we experience similar to that? Well, we think that we live on a curved surface, Earth, a sphere, but since we're very close to the surface, it looks flat around us. That's the same idea here. Being close to Earth's surface is your values of x being close to a. So sorry for any flat earthers out there. I just shattered your worldview. Earth is not flat. Okay, so let's take a look at some basic examples. Just asked to calculate the linearization given a function and an x value. These are kind of plug and chug problems. We need to find two values. We need to calculate f of a y value, and then we need to calculate f prime of a derivative. Recall, derivatives represent slopes of tangent lines. And once we have those two values, we can plug that right into the linearization formula there. All right, so pause the video, give yourself a few minutes to work out these two examples. It is basically just calculating derivatives and then rewriting everything in a new form, the equation of a linearization. Pause the video and check back in a few minutes. All right, welcome back. Let's go through part A. So the first thing is, let's just do the non-calculus part. Given the function, let's plug in our a value, 0. So if we plug 0 into sine of 0 is 0. The next thing we need is the derivative. So if our function is sine of x, the derivative is cosine of x. We're going to again plug 0 into the derivative, and cosine of 0 is 1. Remember, you can get those basic values for sine and cosine of certain angles like 0, pi over 2, pi, 3 pi over 2, and 2 pi going around the unit circle. And if we consider where the angle 0 is, that's no rotation landing on the positive x-axis. The coordinate there on the unit circle is 1, 0. And you might recall your cosine values go with x coordinates. Your sine values correspond to y coordinates on the unit circle, which is where we get those two values for sine and cosine of 0 from. All right, with that, it's just a matter of plugging all this into our linearization. Here we're using a as 0. And if you plug in your values, f of 0 is 0 and f prime of 0 is 1. That simplifies down to a very simple formula for the linearization. L of x is just x. All right, and what this says is that sine of x is approximately equal to x when x is approximately equal to 0. And this is what's known in science and engineering as the small angle approximation for sine. So if we were to plug in a very small number to sine, you should find that it comes out to be approximately that number. All right, if we move on to part B, this one is even simpler. The function is f of x. We can plug 0 in and we get 1. And since the derivative of e to the x is itself, we get for our derivative the value 1. So both the function and derivative values are 1. plug that into your linearization, and we get again a rather simple formula for the linearization, 1 plus x. So what this says is when your values of x are close to 0, e to the x and 1 plus x are pretty close. Now let's use kind of a small x value just to see this. Let's suppose we had x as 0.01. That's, I think, sufficiently close to 0. And if we use our linearization, what we find is that e to the 0.1, plug 0.1 into your linearization, and we get 1 plus 0.01, which simplifying that comes out to 1.1 or 1.10. So that's our value. We get an approximate value for e to the 0.1 using a linearization. Now let's plug it into a calculator because apparently calculators are the be-all, end-all of answers in a math course. So if we plug 0.1 into our calculator, what you'll find is e to the 0.1 has this value, 1.105, and then a bunch of decimals. And if you take a look at the two answers, the approximation we got with a linearization, and then the value from the calculator, they're very close. And that, in some sense, is the essence of how we're going to use linear approximations to approximate certain values, like we kind of mentioned in the beginning. Square root of 4.05 will kind of follow a similar idea using an appropriate linearization. Okay, so before we get to the real example, just using a linearization to do an approximation, let's kind of go through a few steps to make this a little more streamlined for you. All right, to do a linearization, the first thing you're going to need is a function. That's how you're going to calculate the equation or formula for a linearization. You need a function that you can then differentiate. Let's take a look at a few examples of some numerical values we might be asked to approximate. So let's say we have our example from the intro, the square root of 4.05. Now this is a little murky. It's not at all clear how to choose the function, but if you take a look at that value, you might say it is a square root value. And since we're asked to approximate square root of 4.05, let's choose as our function square root of x. All right, suppose you're asked to approximate 1.99 cubed. That's close to 2. So we should say 1.99 cubed is close to 2 cubed. This should be around 8. If we wanted to do this with a linearization approach, since that is a value cubed, let's take as our function of x, x cubed. Hopefully you're starting to see how you might choose the function based off the value you're asked to approximate. All right, let's take a look at one last one. Suppose you're asked to approximate cosine of 0.1. Since that is ultimately a cosine value, let's choose as our function f of x here, cosine of x. One way you can do this in a even simpler way is just replace the number inside your expression with x, and that kind of gives you the function. It's not as useful as what we've been mentioning, but that's a quick way just to replace the number inside with x to get your function. Now, once you have your function, you need an a value to do the approximation at. This would be the point at which you're finding the equation of the tangent line. Now, it's the point at which we're basing or doing the linear approximation. All right, so the second step is we're going to choose a so that f of a is easy to evaluate and is also close to the quantity that you're approximating. I don't have a way to properly define what easy or close mean in this second step, but there might be some basic idea you have for understanding that if we take a look at the examples above. All right, so think back to those 3 examples still there from step 1. With our functions there, f of x that we've determined, let's figure out an a value, an x value, that would be easy to evaluate in those functions. So for the first one, square root of x, we might think square root of 4 is easy to evaluate. And notice square root of 4 is pretty close to square root of 4.05. For the second example, 2 cubed is easy to evaluate, which will be close to 1.99 cubed. So we're going to use as our a value there, for that second example, a as 2. All right, and the last one, this is where you have to be a little bit comfortable with your basic trig values. Cosine of 0 is easy to evaluate. We did that in a previous example. Cosine of 0 is 1. So we're going to think here, cosine of 0 is easy to evaluate, and it should be close to cosine of 0.1. Now, once you have your function and a value chosen, now it's straightforward to calculate the linearization, since we kind of have a formula to plug everything into. Basically, we're just going to plug in a to the function, calculate the derivative, and then plug a into that again. And once you are kind of through finding your linearization, we're going to plug in the x value of the quantity that we're approximating to the linearization. Now, what this would mean with the 3 examples above is whatever our formula is for the linearization, notice the number inside all those values is going to be what we plug in to our linearization. For the first value, square root of 4.05, we're going to plug x as 4.05 into our linearization. For the second example, we're going to plug x as 1.99 into our linearization. And for the third example, we're going to plug in 0.1 to our linearization. Okay, so you might want to copy these steps down to refer to as we go through the examples. That way you don't have to pause the video and go back. And let's get to some examples for how this will actually work. All right, so here's our first real example. The question is just going to ask you to use a linear approximation to estimate a given value. So at this point, pause the video, think of those kind of steps that we just went through a few moments ago, and give this problem a try. You should find that your end result is you get a value for this that is a little bit bigger than 2. So pause the video, give it an attempt, and we'll check back in a few minutes. Welcome back. Let's start off going through this based off the steps that we defined in an earlier part of the video. So since we mentioned we have a square root value here, we're going to choose as our function square root of x. The a value that we're going to use is 4. All right, we can plug in. Maybe for calculating the derivative, you would want to rewrite that square root of x as x to the 1/2, just to make finding the derivative a little bit easier by using the power rule. All right, if we plug our value for a into the function, square root of 4, that's simple. That is just 2. If you calculate your derivative for square root of x, we're thinking of it as x to the 1/2 power. We apply the power rule, and we get down to here. Notice we subtract 1 from the exponent to give us the new exponent in the derivative as -1/2. Now, to make some of the calculations a little bit easier and more recognizable, let's rewrite that derivative with the negative exponent in the denominator. And if you rewrite that, you can express your derivative as 1/2 square root of x. If we plug 4 into there, you should find that your denominator, 2 times square root of 4 is 2. You should get 4 in your denominator, giving you a derivative value of 1/4. At this point, we can just plug in our function and derivative value to the linearization. And if we plug in our two values, 2 and 1/4, we get down to here for our linearization. Now you might be tempted, since you see 1/4 in front of a set of parentheses, don't distribute that 1/4. It's going to make kind of the last step a little bit more work. So keep the derivative value in front of that set of parentheses. It'll make the next part as simple as possible. You might see why when we plug in x as 4.05. All right, so if we do that, we're going to plug into our linearization the x coordinate 4.05. And if we do that, notice the part inside the parentheses gives us 4.05 minus 4. And that's really easy to kind of calculate. Basically, the whole part subtracts out, and you're just left with the decimal part. That's kind of why I advocated to keep the 1/4 out front, not distributing it. It makes the calculations as simple as possible. Okay, and if you just simplify that, what you should find is 1/4 times 0.05 comes out to 0.0125. And what we get is the answer that we were kind of anticipating, 2 plus a small number. And what we find here with our linearization is that square root of 4.05 is approximately 2.0125. All right, now you might not feel comfortable with that. So let's check with a calculator just to kind of have everything sink in. And if you plug square root of 4.05 into your calculator, notice you get pretty much the same values for the decimals up until the kind of like fourth decimal place. These values are remarkably close. The first part we did without a calculator. The second part gives us a value pretty close. All right, that's how we use linearizations to approximate certain values. You're going to build upon this into your Calc 2 course. And as you continue in your science and engineering courses, you'll see this idea of a linearization used in several other places.